Hello everyone and welcome. In this presentation, we are going to address the electron-electron bound state, considering magnetic dipole-dipole interaction. Let's begin by understanding the problem. There are many publications discussing the problem of magnetic interaction between elementary particles with their own dipole moments. Basically, the magnetic interaction becomes significant at sufficiently small distances. Therefore, the problem becomes more complicated due to the need to consider relativistic effects. The equations obtained with the composite potential of the Coulomb and magnetic dipole-dipole interactions, in general, do not have a clear and straightforward analytical solution. This work proposes an approach to study a particular case of electron-electron interaction by numerically solving the M2 equation. The solution to humanity's main modern problems is closely connected with the invention of a new ecologically clean energy source. In recent decades, a new area of scientific research has been intensively developing. We know them as low-energy nuclear reactions or nuclear reactions in condensed matter. However, there is no generally accepted satisfactory theory of the mechanism of anomalous energy release during LENR experiments. Having raised the problem, we discuss a new hypothesis of energy release based on the magnetic interaction of electrons. Strictly speaking, this theory does not fall under the definition of LENR, because in this case, we discuss the interaction of electrons, not nuclei. However, the described mechanism can contribute to the occurrence of secondary nuclear transformations. Let's calculate the composite electromagnetic potential. The potential energy of magnetic dipole-dipole interaction between two electrons can be determined using the magnetic dipole-dipole interaction formula. Formula 2 represents an intrinsic magnetic dipole moment, which is equal to the Bohr magneton, codenamed Formula 3. R is the distance between electrons and μ0 the magnetic constant. Let us rewrite Formula 1 by taking into account scalar products and Formula 2. We will codename it Formula 4. In Formula 4, theta 12 represents the angle between vectors μ for electron 1 and μ for electron 2. Theta 1 and theta 2 represent the angles between the magnetic moment vectors and the line-joining particles. It is clear that the potential energy W depends on the mutual arrangement of dipoles. The mutual arrangements of dipoles displayed in Figure 1 are of interest to us. Cases B and D represent electron repulsion. Therefore, the energy is positive. On the other hand, cases A and C represent electron attraction. Hence, the energy is negative. It is clear that electron pairing requires attraction. Therefore, we can determine the energy W for cases A and C using Formula 4, in which case we obtain 4A and 4C. In this slide, we can observe the position of magnetic poles and spins of electrons for cases A and C. The attractive potential for case C is twice the value of the energy for case A. Note that case A corresponds to oppositely directed electron spins. Therefore, the total spin is equal to 0. The electron spin direction coincides for case C. Therefore, the total spin is equal to 1. The Coulomb potential energy of interaction between two electrons is represented in the formula above. The total potential energy of electromagnetic interaction for case C can be calculated with Formula 5. Let us rewrite Formula 5 to make it more convenient. To do this, we will use the well-known relation shown in the slide, which can be rewritten as Formula 6. Now, substitute values μ0 from Formula 6 and μb from Formula 3 into potential energy Formula 5. Having done this, we obtain Formula 7. Let's rewrite Formula 7 using Hartree atomic units. In the Hartree atomic unit system, the values of physical constants shown in the slide are the ones accepted. Finally, we obtain equation 8 for the composite potential energy of electromagnetic interaction. Let's graph the resulting equation. Here, we can observe the graph of the composite potential energy of electron-electron interaction. As we can see, the obtained potential consists of a Coulomb barrier and a deep potential well, and it has a characteristic maximum. Let's determine the coordinates of the maximum potential energy. R max equals 0.008937 in Hartree atomic units. If we multiply this by the Bohr radius, we will obtain the observed Hartree atomic units. Lastly, if we multiply this value by the Hartree energy, we will obtain the result displayed on the slide. Now we will solve the M2 radial equation for the electron-electron pair. We designated the electron-electron pair by the EE symbol. The EE pair is a hydrogen-like entity, and since the masses of these two electrons are equal, it is necessary to replace the mass, m, with the reduced mass in the equation for the hydrogen atom, codenamed equation 8. Let's rewrite the M2 radial equation for the EE pair, obtaining equation 9. It is difficult to solve the resulting equation using the analytical methods due to the complex dependence of the composite potential. Therefore, we will apply a numerical solution method. Let's observe the numerical solution of the radial equation in the spherical coordinate system. Figure 3 represents the radial wave function of the electron-electron pair, and Figure 4 represents the radial probability density of the electron-electron pair. As a result of the numerical solution of equation 9, the following parameters of the EE pair were obtained. The orbital radius is equal to 0.134876 picometers. Note that this is the distance between the electrons, between the maxima of the probability density. The binding energy is equal to 265,363.7 electron volts. As we can see, the convergence of the equation is very high, which means that there is a high probability that this bound state of electrons may actually exist. Let's observe now the numerical solution of the M2 equation in the cylindrical coordinate system. As we can see, the radial equation 9 includes the angular momentum quantum number L. But as we know, it doesn't include the magnetic quantum number m, nor does it give us a complete picture of the spatial configuration of the electron shells and the magnitude of the magnetic quantum number m. This data can be obtained by solving the equation in the cylindrical coordinate system. The numerical solution of this equation showed us that the convergence is possible only if the value of the magnetic quantum number is m equal 1. We also note that further research is needed in order to obtain a solution for the orientation of magnetic moments for the case A. Most importantly, the possibility of existence of a deep bound state of the electron-electron pair has been theoretically proven. If this theory is experimentally confirmed, it will be further developed. Figure 5 shows the wave function of the EE pair in the cylindrical coordinate system. Figure 6 exhibits the probability density in the cylindrical coordinate system. Lastly, in Figure 7 we can observe the projection of probability density in the cylindrical coordinate system. Therefore, as a result of the numerical solution of the equation in the cylindrical coordinate system, the following results have been obtained. The orbital radius is equal to 0.134793 picometers. Again, note that this is the distance between the maxima of the probability density, which is the diameter. The binding energy is equal to 265,363.7 electron volts. And as we said, the magnetic quantum number is m equal 1. In addition, we see that the spatial distribution of the electron density is represented by a toroid. However, if we take a look at the solutions of the radial equation 9 in the spherical coordinate system, we will see that it resembles a spherical distribution with an empty region inside. Regarding the results and discussions, simultaneous consideration of the Coulomb electrostatic repulsion and magnetic dipole-dipole attraction between two electrons gives us reason to believe that a stable bound state may exist when the electrons approach each other close enough. This is also mentioned by many other authors in their publications. However, it has not yet been possible to obtain an accurate calculation of all the parameters for such a state. In this paper, the possibility of existence of a deep-bound state of the electron-electron pair is proved based on the numerical solution of the M2 relativistic equation. The exact values of the ground state parameters have been obtained. The orbital radius is equal to 0.1348 picometers. In fact, this is the diameter, since the equation is set up taking into account the reduced mass. Therefore, the variable r represents the distance between the electrons. The binding energy equals 265,363.7 electron volts, whereas the total spins and the magnetic quantum number equal 1. The wave functions and probability density distributions have been obtained in the spherical and cylindrical coordinate systems. It has been shown that this distribution is represented by a toroid. This characteristic form of the probability density gives us reason to believe that the EE pair in its ground state is a neutral entity. In addition to the fact that the above calculations and results are of theoretical interest, they may also be of great practical value. As shown, the formation of the EE pair leads to the release of energy at 265,363.7 electron volts. This is of great practical value, which means that environmentally friendly power plants could be built based on this phenomenon. We think there has been provided enough evidence to conduct an experimental search for an elusive particle. To access a link to the paper and a list of publications, scan the QR code. Thank you for your time.